Again. Good afternoon, everyone. It is my pleasure to welcome you to the 5th journal club that Physical Review Letters is hosting since the beginning of the year. I'm Serena D'Alena, one of the editors of PRL, and I was the handling editor of the exciting paper we are covering today. In August 2021, Omar Hurricane, Annie Kreitzer, Alex Zilstrand, Debbie Callan, and their colleagues, part of the Indirect Drive Inertial Confined and Fusion collaboration, announced a milestone for laser fusion. Ignition was achieved at the National Ignition Facility. This result was included in the top physics breakthrough of 2021, announced by Physics World at the end of the year. Of the 1-year anniversary of this groundbreaking development, PRL published the data and results showing that the first controlled fusion experiment reached ignition by 9 different formulations of the Lawson Criterion. Dr. Stephen Obenshain has kindly agreed to moderate the journal club today. Dr. Obenshain is the head of the laser plasma branch and leads the laser fusion program at the US Naval Research Laboratory. The NRL laser fusion program includes research efforts in laser matter interaction experiments, in simulation of direct drive pellet implosion, and in the development and utilization of high energy deep UV excimer laser for inertial fusion. So this is a Zoom meeting, so you know how it works. You can submit questions in the chat during the talk. Steve is going to read them and our panelists are going to reply. We strongly encourage you to make the conversation more lively though, to raise your hand. Steve is going to call your name and you can simply unmute yourself and ask your question directly. Before passing the screen to Steve, I'd like to mention that with the Nobel Prize in Physics assigned in 2021 to Professor Giorgio Parisi for his research and studies in glasses and complex system, for 11 consecutive years, PRL has covered Nobel Prize winning research, and we are looking forward for the announcement in October. To possibly close this cycle. Of course, I will be more than excited to have a plasma physics result covered by the Nobel Prize Committee. So keep going with the good work, people. And Steve, you have the floor now.
Hey, hello, welcome aboard. It's a pleasure to moderate this live discussion of a very important results on inertial fusion. And I'll start by reading off the bios of the panel members as well as the authors of paper. Start with Omar Hurricane, is a distinguished member of the technical staff and chief scientist for the ICF program at Livermore Lab. As a designer at Livermore, Omar has worked on a variety of national security topics, including thermonuclear physics, high energy density physics, explosive pulse power, inertial confinement fusion. He received the Edward Teller Award in 2021. Annie Kreitzer is the hybrid design lead with the ICF program, was lead designer for the shot in 210808, which reached the 1.3 megajoule plus energy. Annie was first employed at the lab as a summer intern in 2004 as an LLNR Lawrence Scholar during her time at UC Berkeley and as a Lawrence postdoctoral fellow following completion of her PhD. She joined the lab in 2012 and has been a member of the scientific staff and now serves as team lead for integrated implosion modeling. Alex Zilstrand led the experimental design for the highest yield NIF indirect drive shot, which will be under discussion today. Alex obtained his PhD from MIT and following work at Los Alamos for 3 years, joined Livermore in 2018. Okay, now it's the members of the panel. There's a broad range of expertise here to cover all the topics that you had to do right to get this good result. Excellent target fabrication, diagnostics, laser illumination, and you have to get the physics right. Debbie Callahan received a PhD from the University of California, Davis, and spent her career working in ICF and inertial fusion energy. Her expertise is in whole room physics and design. She was design physics division leader before retiring from Livermore to join Focus Energy, a startup company working on inertial fusion energy. Andrew McKinnon started his career in the UK at the Atomic Weapons Establishment as a scientific officer, followed by obtaining his PhD at Imperial College London. He joined Livermore in 1999 to work on the Nova petawatt laser. He is currently science leader for NIF Diagnostics. Jean-Michel de Nicola is the chief engineer for laser systems at the National Ignition Facility and group leader at the Laser Modeling and Analysis Group at Livermore. He's responsible for the NIF laser's performance and its enhancements. He is a senior member of the Optical Society of America. Abbas Nikru is the NIF deputy for NIF targets and physics, and prior to that served as manager for target fabrication. He received his PhD from UC Santa Barbara and served for 12 years as director of inertial fusion technology at General Atomics before joining Livermore Lab. And finally, Bruno van Wentegem became commissioning manager of the NIF in 2001 through project completion in 2009, has been operations manager since, successfully supporting all programs on NIF. He has extensive experience in developing laser and diagnostics for plasma research and academia through prior work at the University of California, Irvine, and the Max Planck Institute. He earned his PhD summa cum laude in chemical physics at the University of Leuven in Belgium. And now, Omar, go on with your talk. Omar, are you there?
Can you not hear me?
He's trying to
We can hear you now, Omar.
Okay, that was strange. All right.
Slides.
We see you, Omar.
All right, hold on a second. It's funny, that was working fine. Okay, you can see the slides.
Yes, we can.
And we can still hear you.
And you can still see the slides.
Yep.
All right, something about turning on the laser pointer seemed to shut off my audio. Let me see if, can you hear me now? Super,
Yes.
Okay, let's finally get started. Okay, thank you for inviting us and our team to discuss our result. You're looking at a picture on our title slide of our laboratory looking to the north. The National Ignition Facility, which was part of the cover of the August 12th issue of Physical Review Letters, is shown here, and actually it's kind of in the right location on the superimposed on our lab grounds, because the facility is in the northeast corner of our lab. The facility itself is a laser about the size of 3 football fields. The target chamber is about 10 meters in diameter, and it's right where I'm pointing here. And inside that target chamber is where all the action goes on. And at the center is a target. The target that we generally use for indirect drive experiments looks something like this diagram on the upper left of my slide. There are 2 main components to the target. There is a central capsule, which is a spherical hollow capsule where the outer layer of the capsule is a material that we call the ablator. Inside, on the inside surface of that capsule is a DT fuel layer that's held at cryogenic temperatures. It's basically DT ice, and central to that capsule is the DT gas, and that's basically our fusion fuel. The capsule is surrounded by a metal volume that we call a hull ROM. that has two apertures at the top and bottom where laser energy enters. And this entire object is what we call the target. And the capsule, again, is just the central part of it where most of the action takes place. The way indirect drive works is the laser energy that comes from our facility is not directed at the capsule. It's actually directed at the inside walls of this hull ROM. The laser light is absorbed at what we call the critical surface, where the plasma frequency of the material roughly matches the laser frequency, sometimes a quarter of the laser frequency. The laser light is absorbed and then re-emitted in the form of X-rays. And then the X-rays fly in all directions and fill the volume of this hull ROM. And those X-rays touch the outside surface of the capsule and are absorbed, causing it to ionize that material and produce large pressures. And we call that plasma that's created in that X-ray absorption process the ablated plasma. The ablation pressure is related to the materials that capsule is made out of. It depends upon the atomic mass, the atomic number, the radiation temperature that we're able to achieve inside this hull ROM, and that's part of the design process. And there's also an albedo, which is the tendency of that ablator to reject some of that X-ray energy back towards the hull ROM. Because we're taking material, ionizing it, and bringing it to high temperatures, the pressures associated with ablation are very high. For us, typically, there's several hundred millions of bars. And a bar just is a 1 atmosphere of pressure. So this is 100 to 200 million atmospheres of pressure. Because of the pressure being so high, we're actually able to accelerate the fusion fuel that's carried on the inside of this capsule to extremely high velocity. And that's basically the basic principle that we're going to use to get to the conditions we need for interesting fusion to happen. Of course, these large pressures, which are about 1,000 times higher than what you would get from high explosive, also generate shock waves. And so inwardly directed, as the radiation temperature of the hull ROM increases, there are shock waves that travel inwards, and they push some of the ablator material, and they shock also some of the DT fuel as this process proceeds. Okay, indirect drive is actually very inefficient energetically, and the point of actually our system is to knowingly trade energy for energy density. And we do that because implosions act like pressure amplifiers. So again, here's our generic target. We're shooting the laser energy into the hull ROM and getting that X-ray conversion process. For us, we're using 3 omega, 351 nanometer light from the NIF facility, and we're generally delivering, in the case of the experiment we're talking about today, 1.9 megajoules of energy. And as we just discussed, that energy is turned into X-rays, and some of those X-rays touch the outside surface of the capsule. Because the outside surface of the capsule in terms of surface area is very small compared to the surface area of the hull ROM, we don't actually absorb that full 1.9 megajoules of energy into the capsule. We get something that goes more like the surface area ratio of the capsule to the hull ROM. So it's about 1/10 of the energy from the laser being absorbed into the capsule. But as we said a moment ago, that actually causes the outside surface of the ablator to explode, and we create that several hundred megabar pressure that drives the capsule inwards upon itself, accelerating it to very high velocity. As the ablation proceeds, though, we end up expending about 95% of that ablator material. We actually turn it from solid state into a plasma, and that costs energy when we do that. And we expend a lot of energy that's absorbed in the surface in that process. So by the time you get to the final state where the fusion fuel has been compressed up to high density and high pressure, only about another 1/10 of the energy absorbed by the capsule is actually inside the fuel. So we've sacrificed a couple of decades of energy in this process and going from where the laser is shooting at the target to what's actually in the fusion fuel. But again, we're doing that knowingly because we're using this pressure amplification process, going from several hundred million atmospheres of pressure to several hundred billion atmospheres of pressure. And that's a key part of what we're doing. And this whole process is what we call indirect drive. Because this process is very energy inefficient, There are a number of different gain metrics that we use that are comparisons of the fusion yield compared to these different stages of the target operation. So we have something called the target gain, which is a ratio of fusion yield to laser energy absorbed, which is this initial phase. We have the capsule gain, which is the fusion yield compared to the energy absorbed by the capsule. And then we finally have fuel gain, which is the fusion yield compared to the energy delivered to the DT. And these gain numbers will come up near the end of the presentation. Okay, so why do we do this? Why do we sacrifice so much energy for this pressure amplification process? And it has to do with the fact of what we're trying to do with our DT fusion reaction. So we're taking deuterium and tritium, which are isotopes of hydrogen, and we're trying to combine them under high pressures and densities to create a copious amount of fusion reactions. And DT fusion produces a 14 MeV neutron, which is basically 80% of the energy of the fusion reaction is carried away by that, and an alpha particle, which is a helium-4 nuclei, which is about 20% of the energy. If you look at the reaction rate of this reaction, it increases as a strong function of temperature. It's this blue curve here. There are other nuclear fusion reactions shown on this plot, but the blue one is the one of interest to us. And what you can see from this plot is if we can get our plasma to heat, we can get the reaction rate to increase. So the idea behind what we're doing is we're trying to capture some of these alpha particles inside our fusion plasma and keep some of that heat that's generated by the fusion reaction itself. If we're able to do that and capture some of that heat, we can get the temperature in the plasma to increase. And if we can get the temperature in the plasma to increase, we can get the reaction rate to go up. If we get the reaction rate to go up, we can get more DT fusions to occur. We can get more alpha particles to be generated. And if we're able to capture some of those inside the fusing region, we can get the temperature to go up again. And if we get the temperature to go up again, we get even more reactions. So we can get a very rapid increase in the number of fusion reactions if we're able to hold on to some of these alpha particles that are carrying away 20% of the energy. The way we do that is when we, in our system, where the target accelerates the fusion fuel high velocities and then compresses it, we're able to generate a central hotspot. For our typical case, we're able to stop about 70 to 80% of the alphas in that hot plasma region. And that hotspot itself is surrounded by a cold cryogenic, or what was the cryogenic DT fuel, which is much higher density than the hotspot, but much cooler. Alpha particles that are not stopped in the hotspot hit the DT fuel, and that causes ablation of the fuel from the inside out, and that adds mass to the central hotspot. To get this ramp-up process that I was just describing a moment ago, we need very extreme conditions. And so the conditions that are needed are areal, what we call areal density, rho R is the term we use, of over 0.3 grams per centimeter squared, a central hotspot density of over 100 grams per cc. And keep in mind that the cryogenic fuel started at 0.25 grams per cc. So we're actually compressing the density extremely high, and things like gold or other high density metals, you know, the density is about 19 grams per cc. So this is many times the density of the solid materials, of the most dense solid materials you're familiar with in your daily lives. And of course, we're trying to get pressures of several hundreds of gigabars, about twice the pressure at the center of the sun. Okay, so how do we get these conditions? Getting these conditions actually requires a delicate engineering and understanding of the power balance inside our fusion plasma. And so this is a plot on the left, shows a simulation of a stereotypical implosion. This comes from one of our hybrid E experiments that Annie designed. On the left of this image is density. And it's not a perfect shell. This actually shows some of the morphology defects that we deal with when we're trying to do one of these implosion experiments. But you can see there's high density outside. That's the cold fuel. And then there's a low density inside, which is our hot plasma. On the right side of this plot is temperature. So it's high temperature in the middle, cold outside. There are a few key processes that are throwing energy around inside our fusion plasma, and we're trying to, again, engineer that ramp up process to happen by controlling these processes. The key process that we want is alpha heating. This is the power per unit mass. It goes as a function of density and a high function of temperature. And if you get a lot of that, you can get the temperature in the plasma to go up very quickly. Competing against that alpha heating is bremsstrahlung losses. When you make a plasma hot, it radiates X-rays. The power per unit mass of the radiation that comes out goes to the density times the square root of temperature. And then finally, when you make a plasma hot, thermal conduction wants to carry energy away, and the power per unit mass that allows you to calculate how that energy is being carried away goes as a high power temperature, but it goes down as the areal density of the plasma goes up. So the power balance of our plasma is controlled by these processes that take energy and put energy into the plasma, and processes that carry the energy away, and that controls the time rate of change of temperature of the plasma through a heat capacity that we know for dT. So the other key process that actually gets the whole thing hot in the first place is this implosion process, which is a result of that ablation physics that we discussed earlier. The implosion process allows us to actually very rapidly shrink the volume of our capsule and accelerate it to high velocities, and that allows us to get high kinetic energies. When that happens, we get PDV work, and that's this source term which drives everything into our implosion system. The PDV work rapidly increases the temperature of our plasma as we accelerate it to velocities of several hundred kilometers per second. And as that temperature increases, then energy is redistributed between alpha heating, Brem's losses, and electron conduction losses. And we're fighting those losses to try to get to a state where the alpha heating takes over. The problem for inertial confinement fusion, and this is one of the processes that distinguishes it from magnetic fusion, is once that implosion reaches a minimum velocity where the pressures are many hundreds of billions of atmospheres, you can't hold on to that very long. So it naturally wants to blow itself apart. So it explodes. And as a result of that explosion, this PDV work that was the source of heating in our plasma now becomes another source of cooling that makes it even harder to achieve the conditions that we want. And it's yet another energy sink that's fighting against this alpha heating term. And magnetic fusion generally doesn't have to deal with that. As a result of these competing processes of sources and sinks, and the way this PDV work changes sign after peak compression, the nature of an implosion is highly impulsive, and the period over which we can get the DT plasma to the conditions we need is a very short duration of time. And it's a delicate balance between the alpha heating, the PDV work, the conduction losses, the radiation losses, and getting that conversion of kinetic energy into internal energy. Okay, so why are we trying to do this? We're trying to get two key states or two key milestones that basically tip the balance of the sources and sinks in favor of the sources. One of those states is what people call a burning plasma, and a burning plasma means that the net alpha heating that's going on in our plasma is more than the heating that we got from the PDV work, which is our injection of energy into the system. So going back to this power balance equation, a burning plasma mathematically is defined as essentially when this term here dominates over this term here, but this is a time-dependent expression, and as I just said, the plasma is behaving very impulsively, so this statement makes more sense under an integration. But again, it just means that the alpha heating is dominating over the net PDV work, and that's what we call a burning plasma. And the same definition essentially applies to magnetic fusion. And in fact, in magnetic fusion language, this is most similar to the statement of Q alpha greater than 1. Okay, but what we're really after, and what is the topic of today's talk, is ignition. And from Lawson's statement, ignition is the state of a thermal instability where the plasma now has the alpha heating greater than all losses, including that PDV work loss for a duration of time. So looking at this equation again that determines how the temperature of the plasma heats, if we could somehow arrange or engineer the situation where the Brem's loss, the electron conduction's loss, and the PDV work loss are small compared to alpha heating, then these terms dominate. When these terms dominate, the basic behavior is a finite time singular explosive increase in temperature because the time rate of change of temperature goes up as a rapid function of temperature, and that's a thermal instability. It doesn't take place instantly, though, because of the heat capacity here. It takes time for the plasma to heat up, and that's why time is important. We have to be able to hold it together for enough time for this instability to take place. The time scale of interest is generally many tens of picoseconds, something like 50 picoseconds or so, although it depends on temperatures and densities. We call that time the bootstrapping time. In order to engineer this situation, we need high temperature, high rho R, high pressure, and high temperature and finite time. And we were able to do that. And Annie's going to describe how we did it now. Annie?
All right, can you hear me?
Yes, you're coming through fine.
Okay, great. So hybrid E, the design that resulted in the papers that we're talking about today, is the first ICF design to obtain a burning plasma first and then ignition in the laboratory. And this was done by increasing the energy coupled to the hot DT plasma. And this was a major challenge here because the designs that were done previously were maxed out in driver energy and driver power. And so that was the main challenge here, is how do we increase the scale of the implosion without any extra driver energy. So if we look at the left-hand plot here, to achieve ignition, this requires careful optimization of both the Hallraum and the capsule implosion physics together to maintain the high energy density that Omar just talked about. First, we need to keep a low adiabat. So we need to keep a dense DT fuel piston to do sufficient work on the hot spot. We need to maintain implosion velocity so that we can convert that work to hot spot internal energy. And we also want to maintain a low coasting time. So the coasting time is nominally the time where the laser drive falls off relative to the minimum volume. So we don't want it to coast in. And that affects the implosion pressure as well as the energy density. We also want to maintain good stability. So if we have mixing at interfaces or seeds for mixing, that can send a ablator material into the hot DT plasma and reduce the DT plasma temperature. And in addition, we need to maintain sufficient low mode asymmetries. So if you have something that looks like this in the bottom right-hand corner, that does insufficient work on the DT, the hot DT plasma. So all these terms tend to trade off of each other. So what's good for one is generally bad for the other. And if we go back a slide, Omar, okay. And in addition, what's good for the implosion is generally harder for the Hallraum to do. And so I'll be talking about on the right-hand side here, one of the main improvements or trade-offs we made to field these larger scale implosions. So to field a larger capsule to the same implosion velocity, which has more mass without having more driver energy to do this, we needed to develop more efficient Hallraums. And so we did this by squeezing a much larger capsule into just a slightly larger Hallraum. And the issue with that is that that makes the symmetry of the radiation drive very difficult to control. There's less room between the capsule and the wall, and you get a drive deficit at the waist of the Hallraum, and that gives you an elongated implosion, and you don't do sufficient work on the hotspot. This is also very difficult to calculate, this late time symmetry. And so a couple of key aspects here is we used data-driven models, the Debye curve, to guide our design choices for achieving symmetry. And that is a semi-empirical formula fit to a large set of NIF experimental data that we've obtained over the last many years. And in addition, we move energy between laser beams here to control the radiation symmetry, cross-beam energy transfer, and doing that in low gas filled hull rooms. So the hull rooms are filled with helium gas to hold back the wall. But at high gas flow densities, that was impairing the efficacy of cross-beam energy transfer. So doing that here in low gas fill hull rooms was a key aspect. So if we go to the next slide. So then moving from the burning plasma regime to the ignition by Lawson Criterion, we made additional improvements to the hull room efficiency, and this enabled further optimizing the coasting time. So what we did here is we reduced the size of the laser entrance hole, the hole at the end of the hull room where the beams enter, and we didn't reduce it by all that much. If you can see down there, the newer design is on the left-hand side and the older design is on the right-hand side. And small changes like that make a big difference in available laser drive, as well as make it much more difficult to control the symmetry. So we had to make a few more changes. We had to move the beams around so they didn't clip the LEH, and we had to regain the low mode symmetry of the radiation drive through changes to the cross beam energy transfer. So with a more efficient hull room, that enabled us to achieve the same peak radiation temperature at lower laser power. And this enabled us to tack on that power to the back end of the pulse, effectively extending the pulse in time, so keeping the drive up late in time compared to when the implosion reaches minimum volume. So reducing the coasting time, and that helped keep the hot spot pressure high. So these changes resulted in an 8-fold increase in yield and allowed us to access a higher hotspot temperature and ROR regime, so higher energy density. And there is a couple of other changes which I'll talk about next, but if we look at the plot on the left-hand side, this is the hotspot trajectory as a function of time for a few different regimes. If we look at the lower curve here, 170601, here we just start to see alpha heating balancing the Bremsstrahlung losses, but it's not really enough to get going and the hotspot disassembles. And then the curve in the middle there is the burning plasma regime where alpha heating is starting to dominate over the energy balance equation, but again, it's not quite enough to get going. And then the curve on the top is the latest experiment where we sort of see a fundamentally new behavior, substantial increase in the hotspot temperature and ROR, and we actually see a reversal of trajectory where we're burning at lower ROR or on the way out as the implosion is expanding. So on the right-hand side is a plot from the PRE, which shows the changes that were made going between the previous burning plasma regime and their impact on yield, on neutron yield versus 210808. This piecing apart is done in calculations, but the calculations are tuned to match the experiments, and then the model is held constant. So there we have the data of the previous burning plasma regime, which matches the first bar, which is the experimental post-shot, the simulated post-shot. Then we take out the impact of low mode asymmetries, and it's not significant for this regime, for this experiment. But then we see a several-fold increase in the performance due to the lower coast drive. And then the next bar over shows about the same amount of increase due to better stability. And that's a combination of the lower coasting drive provides a better Atwood number. So you have less Rayleigh-Taylor mixing at the fuel and ablator interface, as well as an improvement in capsule quality. And so experiments that were done this year are to piece apart the relative impacts of both of those things. So we, for this experiment, we fielded much higher capsule quality than ever before on the NIF. So that's where that comes from. We also reduced the size of the deuterium tritium field tube that sticks into the capsule from 5 microns to 2 microns. And that's important because that perturbation in the capsule can seed hydrodynamic instabilities, send material into your hot DT plasma, and reduce the temperature. Here in this regime, it did have an impact, but it wasn't as large as the other things that I just mentioned. And then adding back in the low mode asymmetries we had on 210808, because we did still have those asymmetries present, then we can regain the performance that was measured from the experimental, from the experiment. So if we go to the next slide, going back to the plot that Omar showed, so we can look at simulations and see what the calculated hotspot energies are as a function of time. And as Omar mentioned, we need to have self-heating, which outweighs all the energy losses and for a duration of time, so Lawson Criterion. The picture in the center is from a Hydra calculation. Actually, the plot on the right shows it includes the low mode asymmetries from the previous slide, so the best match to our measured implosion metrics. And here we can look at the PDV work, and that's a black curve. That's the work that's being done on the hotspot as a function of time. And the internal energy, the blue curve of the hotspot directly follows the work that you're doing on it early in time. It starts to rise up beyond that curve as the alpha heating is starting to also do work on the implosion and increase the internal energy of the hotspot. And then here, the red curve is the radiation losses are starting to come up as the plasma temperature is getting hot, and also the conduction losses. But something that's interesting here is that even though those loss terms are coming up, we still see quite a significant increase in the internal energy of the hotspot. And that's also well beyond when we see the explosion phase. So where the PDV work term rolls over and starts to go the other direction, we're actually, that's becoming a sink. So we're losing pressure, we're losing work on the hotspot as the implosion is exploding back out, but yet due to the significant amount of alpha heating, we still see the internal energy rise after that and peak later in time. So the alpha heating is completely dominant for that experiment, which is a new regime that we haven't seen before. So that'll pass to Alex.
Okay, yeah, thanks, Annie. So in addition to looking at these things with the simulations, we want to be able to infer the burning plasma and Lawson criterion based on the data. And so NIF has an extensive suite of diagnostics. Just as an example on the right, this is actually from a different experiment, but we have imaging diagnostics on multiple axes, looking at neutrons, looking at X-rays. By combining combining the multiple axes, we can do things like reconstructions. You see in the center, this is a very nice 3D reconstruction of the neutron emissivity from a NIF experiment, even though the scale is only a few tens of microns. And so we measure everything that we can, but unfortunately, there are a few things that we cannot directly measure, and so we have to infer them. So as an example on the left, this is an expression for the fusion yield, which depends on the density squared, the reaction rate, which is a function of temperature, the volume, and the duration of the burn. And so we can measure most of those things denoted by the blue arrows, but the density we cannot measure directly. And so we have to infer that basically by inverting this equation. And so we do that for a number of the hotspot properties, the density, areal density, pressure, energy, and so on. And so you can see the papers for more of the details on this. If you go on to the next slide, we feed those that mix of directly and inferred quantities into different formulations of the Lawson criterion. There's actually a number of ways that people have formulated the Lawson criterion for inertial fusion in the literature. So we went through 9 of them in the papers. We're just showing a few of them here, but essentially those become contours in different parameter spaces. So for example, pressure and radius on the left from a criterion by Lindell et al. And you can see on the other plots different criteria for p-tau and temperature. And on the far right, this is the yield amplification, which is essentially how much the yield is increased from self-heating versus 2 other parameters. And so in all these cases, the dashed curves show you where the Lawson criterion is satisfied above and to the right of that. And so the previous data on NIF are shown by the points. They're very clearly below those criterion. For 210808, we show that as a little probability distribution there. And so we can feed that into an assessment of the likelihood, based on this inference methodology that that experiment satisfied the Lawson criterion. And so, as you can see just visually here, this is the first NIF experiment that is clearly satisfying the Lawson criterion. If you go to the next slide, this is just a little bit more look at some data. There's a number of very interesting observations that we go through in the publications that are novel for this regime. So for example, this is a comparison on the left of X-ray and neutron images from two burning plasma experiments, 210207 and 307, compared to the igniting shot and 210808. You can see it's actually quite a bit larger. So the volume is approximately doubled. And that is actually a signature of ignition. So that's a signature that the peak emission is coming during the explosion phase, like Omar talked about. Alpha heating is overpowering the loss mechanisms. And so this is on the right is a table from the paper. I won't talk through all of this, but just to highlight a few things with gains. So inertial fusion is actually very inefficient at heating the DT fuel. Only about 1% of the laser energy goes into heating the fuel. And so if you look at the gain in terms of fusion energy produced compared to the energy input to the DT, you actually get quite high numbers. It's about 75 for this experiment because the heating is so inefficient. This is the first experiment where we've had what we call capsule gain. So the fusion yield was about 5.8 times the amount of energy that was actually absorbed by the capsule. But if you look at the total laser energy delivered to the target, the fusion production is still less than that. So the target gain is about 72%, as you can see there. And if you go on to the next slide, I think this is our summary. So just a few concluding remarks here. It's been obviously a very long road to get to where we are. Many decades of work by the ICF community. In many ways, it wasn't as easy as originally envisioned, but we've been solving problems in steps over the years and decades to get to this point where we have a significant advance for the first time. So shots about a year or two ago passed the burning plasma threshold for the first time. That was published in Nature. And then subsequent to that, we did this experiment N210808, which is covered in the 3 papers in PRL and PRE. It was the first shot to achieve capsule gain and passes several different formulations of Lawson's criterion for ignition. So this is the first ignition experiment in the laboratory. It had a target gain of about 70%. There's a different definition of ignition that was published by the National Academies in 1997 that equates target gain with ignition. Just as a point there. We've been, obviously we've been busy since then. There's been some challenges trying to reproduce 210808 based on some challenges with the target quality is one of the leading candidates. We do actually have kind of a hot off the press tidbit here that we had a shot just a week ago in which we made some changes to utilize a higher laser energy that produced some very promising results. We're still working on the data, but stay tuned on that. Probably we'll show more at the DPP conference in a few weeks. And so we're continuing efforts to increase the performance farther, improve the robustness so it's more repeatable. But the bottom line is that this is essentially an existence proof that fusion ignition is possible in the laboratory. And so with that, I think we'll go to any questions.
Okay, there's 2 routes to questions. One is in the chat. I don't see very many yet. Does anyone want to raise their hand and ask a direct question?
I raised my hand.
Okay, go ahead. Who
What
are you, by the way?
Oh, this is Bruno Coppi. Did you make any progress in understanding non-thermal effects that may have played a role in the ignition shot? You know, you had experimental evidence that neutrons were produced that were non-thermal.
Can you hear me?
Yes, thank you.
We have done some experiments with the dudded fuels that we call THD experiments that by design have almost no alpha heating going on. And we see the same non-thermal signature in the neutron time of flight. So at this point, it appears from that data that that non-thermal signature in the neutron time of flight is not due to alpha heating per se, but there's some other process going on that we have yet to understand. So our understanding, I think we still haven't really identified the physics behind that, but we have done these no alpha experiments that imply it's not necessarily alpha heating that's causing it. I don't know if anyone else has anything to add on that, Alex, or?
Yeah, I think it's essentially a work in progress understanding that observation. I think there will be a publication and some talks at the DPP. And I think I would emphasize that it is sort of a subtle signature. It's not that the peak of the neutron spectrum is a significant deviation from what you would expect from a thermal distribution. So work in progress on that.
Okay, there seems to be a few questions. Basically, how do you get from here to commercial use of this ignition result, which, aside from all the other many things, is to get the gain up? Does anybody want to field that?
You want me to talk about that, Omar?
Sure.
It's fine, go ahead.
So as Steve mentioned, following this result, I moved to a startup company that's looking at inertial fusion energy. Remember, NIF was never really designed for fusion energy. And so now the idea is to take this result and what we've learned from this result and try to move towards fusion energy power plant. There's a lot of challenges, and that is, I think people understand. As Omar and Alex both talked about, the target gain for this shot was, less than 1, which means you don't have any electricity to sell. You need target gains that are well in excess of 1, something like 100. And so the focus for this company and other companies, I think, that are looking at this is, we've got to make it more efficient. And to do that for the company that I'm working for, we're using a little bit different scheme for doing ignition called fast ignition, which has the promise of higher gain. And then you also need to work on the technology. You need a rep-rated laser. I think someone mentioned in the chat, you need to be able to inject targets at a high rep rate and build targets at a high rep rate. So those are the kind of challenges that we need to face if we want to take this result and turn it into a fusion power plant. And there's a lot of excitement in doing that right now.
I would add that the NIF result has increased interest in various approaches to high gain inertial fusion for energy. So it's been very helpful. Okay, we'll give you one from Steve Bodner, who wants to know, how do I know this is a thermal effect rather than a beam plasma effect? I think you guys think it's thermal, but why don't you answer your old friend, Steve? Someone. Annie?
Yeah, I think that was kind of the first question, right? That we already had discussed, that we don't see this happening in the no burn experiments. Is that a sufficient answer, or should we continue discussing?
I think maybe one quick thing to add on to that is that when we do the dudded fuel burn off experiments, those validate the modeling that the yield is increased by about a factor of 30 due to the self-heating.
Okay.
I just wanted to ask, I missed the beginning of the talk, and I was wondering what the source of the alpha particles are.
They're a product of the DT fusion itself. So DT fusion produces neutrons and alpha particles as it proceeds. Those are the byproducts.
I guess there's other questions. Oh. Okay, this was a statement from Annie Christer on, I guess, what is the bottom line of what you guys think is limiting the gain from 1D? Is it non-uniformities, low mode non-uniformities, defects in the targets? What's sort of the thinking right now?
Sure, I can answer that since I already threw something in the chat. So for 210808 itself, we still think that there is a reduction from the low mode asymmetries, and also swings in the low mode asymmetries, which we recently measured in tuning experiments and are looking into trying to improve. Following 210808, we've observed an increase in the amount of emission that we observed, which we correlate to mixing of the ablator material into the hotspot. And that reduces the temperature of the DT plasma. And then on a couple of the experiments, we had an anomalous mode 1, which can be a result of, thanks Omar, the jargon, can be a result of non-uniformities in the laser delivery, non-uniformities in the capsule thickness. We have windows in the hull ROM that can also contribute to a mode 1 asymmetry. So it shoots off in one direction. So we actually measure both of those degradations, and we've been able to directly correlate that to reduction in performance. And actually the modeling agrees really well with that as well. Better than I thought it would. And that kind of hits on one of the other questions, which is the theoretical point or position of the ignition cliff. And so the fact that we're getting the reduction in performance as a result of the degradation mechanisms accurately modeled in the calculations is a good sign for that.
Okay, somewhere in here, someone wanted to know how much your targets cost for IFE. We got to get down like a quarter per target. Where are you guys right now? Nicola, is he there?
I think that's a question for Abbas if he's on.
Yeah, okay. That's an Abbas question.
Yeah, I'm sorry. If you have a question on laser, target is for Abbas.
Yeah, I know. I know it's expensive. It's nowadays. Okay. Does anybody else want to raise their hand and ask questions? If not, I'll ask one, and that is right now it appears you have very good simulation capability for the capsule itself. The whole room remains very complicated, and where do you see the future to that, of being able to simulate that? I guess that's you, Annie.
Yeah, okay, so sorry, I was answering something in the chat. So how are we going to make progress given the fact that it's difficult to calculate the hull room symmetry, et cetera? So we are still relying on the analytical model that's fit to a wide range of experimental data at the NIF, and that's been quite effective in getting us to basically enabling us to know what delta lambda. So between the laser beams, we change their wavelength to transfer energy, and so we can determine that pretty accurately from this this model. Okay, reproducibility. So there is some reproducibility issues with the low mode asymmetries that are intrinsic, but that hasn't been the main limiting factor recently. The odd mode 1 asymmetry was worse on a couple of the first 2 repeat experiments, but since then hasn't been that bad. Did I answer the entire question? So I also threw in the chat directions we're going to try to improve the temperature and density of the hotspot. And we believe that we have the predictive capability between where we trust our models, as well as Debbie's model for hull ROM, for achieving hull ROM symmetry to get to those points where we want to go.
Why don't the capsules reproduce?
Is Abbas not on? You know, the capsule seems to be like baking bread. And if you bake bread and you don't get the water composition right or the temperature right, you're not going to get the same morphology of cells in the bread. So it's kind of very much a recipe at this point. And the target engineering group is working on understanding the sources of imperfections and a lack of reproducibility in the capsules. Dirt in the target fabrication process is one of the things they're looking at. So, it's the same way when you cook. You don't get exactly the same thing every time.
Okay. I'll just add on a positive note that they've made quite a bit of progress in the last couple of weeks to a month in determining how to fix this dirt problem, essentially, which they think is related to the temperature that they do the coating process at.
I would like to make a comment on the meaning of ignition for magnetic confinement. There is some confusion in your original paper. It is very important because if you don't get close to ignition, the auxiliary heating system would be enormous. So the rumor that ignition is not important for magnetic confinement is not correct. It's important both academically and practically.
This is from an advanced tokamak guy, right?
Right. Well, the difference is that you can make non-thermal plasmas with magnetic confinement, but you do need ignition.
Okay. What sort of gain do you think you could get with ignition?
You mean with magnetic confinement?
Yes, yes.
Well, the gain would be very large, you know.
Okay.
Because there you are long times available. But the problem is that with those experiments, we are very far from ignition.
Thanks, Bruno. I think you're referring to one of the comments we had in the introduction to the PRL.
Yes.
I guess we were trying to be kind to magnetic fusion. So
I think Bruno is you may be kind, but are incorrect.
That's right. It's a very, very important result. I don't need to convince you.
Okay, just from me, is the target fabrication harder with the diamond than plastic? Do you see all these, I presume, bubbles and so forth, or impurities in the diamond that is not as much of a problem, at least with the plastic?
Again, Boss is really a question for Boss. I don't think he's on. They're different. Every capsule has its own peculiarities. We do not have the same sort of defects in plastic as with HDC, because HDC is a crystalline ablator.
Right.
Plastic is an amorphous ablator. But we do have other problems with plastic, including a sensitivity to UV light, which apparently causes it to absorb oxygen in the presence of UV light, and it changes the surface roughness. You know, for that little bit of surface that had been exposed to UV light. And in particular, there was an issue where the glue that they use to hold the fill tubes in the capsules, it's an epoxy that is hardened with UV light. And we've actually damaged the capsule in the vicinity of that glue dry. So everyone has its own pros and cons.
That's useful for us to know that want to do direct drive with plastic capsules.
Hello, Steve. There were two hands raised. One was Bob Zwaska a couple of times, and the other is Max Karasik. I mean, Max,
okay. Why don't you read out their questions?
They raised their hands, so they can just unmute themselves and ask the question.
Okay.
Max, do you want to start?
Sure. I wanted to ask a little bit about the gas fill. Is there are people looking at trying to go to higher pressures, back to higher pressures to maybe relieve some of the asymmetry issues to have more symmetric low modes? Would that be useful? Is there ways to go there?
Are you asking about the gas fill in the whole ROM?
I think that was a whole ROM question. Yeah.
Do you want to take it, Debbie, or?
Either way, Annie, you can take it or I can. You know, when we had high gas fill, we started with high gas fill whole ROMs on the NIF. Those generated a large amount of laser plasma instabilities. And so we backed off to this kind of low gas fill regime, which seems to be more predictable and easier to control with less LPI. You know, maybe in the future we would go back. But I think for right now, you know, the focus is still on the low gas fill. And Annie, you can correct me if that's wrong. It was just very hard to predict the laser plasma instabilities.
Yeah, that's true, Debbie. I think we're going to sort of push the crossbeam energy transfer in the low gas fill ROMs as far as we can. We also have shaped Hall ROMs. So we have the IROM and the Frost ROM, which are designed to help with low mode asymmetry, which we're currently working through right now. There is always that background thought of if we go higher again, but not too high, can it help? So it is still, it's very difficult to model. And most of our data that we've tuned the analytical model to is at 1 gas fill density. But it is a possibility.
Bob, are you there?
Yes, I am. Thank you. My question is how do the results of this have bearing on perhaps future direct drive experiments? Is there much prospect for that?
Well, my comment would be the implosion physics is actually very relevant because the implosions are at some level kind of fundamentally the same. One of the implications is we and our colleagues who do direct drive experiments have had trouble controlling what we call low adiabat high convergence implosions. And so part of our set of tactics that allowed us to get to this result was to use more moderate convergence, higher adiabat implosions. Why we are frustrated when we try to do very low adiabat implosions, which I'm using a jargony term. Adiabat is basically a measure of entropy in the implosion, and a low adiabat implosion allows more compression than a high adiabat implosion. What is frustrating us there is not clear, but we just know experimentally we're just much better able to predict and control the higher adiabat implosions. And the implication for that is really if you want really high gain, you really need to make a low adiabat implosion work. And that's something that's going to take some better understanding to be able to achieve that. And that's true of indirect drive and direct drive.
Okay, thank you.
Michelle Wei?
Oh, yeah. Congratulations for the big breakthrough, and also congratulations for the recent online shot. I'm just wondering, what's the pre-shot prediction on the yield for the online implosion with the thick ablator and a high laser energy?
Yeah, I'm not sure how much we're supposed to be talking about this at this point. I will be also talking about this at APS. That first experiment was it was interesting because we've now been able to achieve high yields together with target quality that's worse than 0808. It had many defects in it. So we're trying to quantify what that did to the mixing, but the pre-shot predictions would have been a factor of 2 to 4 higher than 0808. Yeah, it's similar, but we believe that's because of the target quality. And so in January, we plan to, in the same configuration, field high quality targets that have recently been made.
Great, yeah, thank you.
Terry?
Well, first, very impressive work. I was especially impressed by the alpha heating progress and how much that's gone. It looks like a really nice potential. I just had a small question looking more towards long-term. How the lasers hold up in this? Are the lasers extremely durable? Do they have some issues about lifespan as you get into higher repetitions? So I realize it's a little bit tangential, but I was curious about that for the long term.
I can take that one, Terry. Is your question really directed to the NIF short term, or are you talking about longer term application with high rep rate lasers?
I'm wondering if what's going on right now is giving data that will then become relevant for the later high repetition, because obviously high repetition is going to be a necessity. Right. So if the lasers are, for instance, are failing at a significant rate in a lower frequency, then obviously that would be a concern later. Again, it's more of a long-term question.
Right. Well, I can address the short-term questions. I think the NIF laser is holding strong. As a matter of fact, that Annie and others alluded to, we increased the laser energy on the most recent ignition experiment, and we think we will be continuing to do so. At the other end, NIF has been built about, some time ago, and 2001 when was first commissioned, and what we call the master oscillator room, which is the front end of the laser using telecom industry devices, was recently refurbished because it was aging and we were encountering issues of not being reproducible, and we wanted to increase the symmetry of the experiment and the shot-to-shot reproducibility. So to your question, it was not really a failure. It wasn't definitely not related to running at higher rep rate, even though our front end runs at 960 hertz. But it's part of the modernization of the facility that was built about 20 years ago already. So,
I'm just curious, what laser technology are you using? I'm sure it's in the papers. I'm just neodymium doped aluminum.
Correct, neodymium doped glass, and to that effect, you can refer to, we published a comprehensive issue on the Fusion Science and Technology review in 2016. So there are about 400 or 500 pages. We're using flash lamp pumped technology, which obviously wouldn't be suitable for operations at high repetition rates that would be needed for IFE application, like in the 10 hertz or beyond that.
Thank you.
Okay, any more questions? I'd encourage people to raise their hands and ask the questions directly. Any more comments or observations that the NIF crew would like to make?
Well, I would just like to thank everybody for their interest in our papers, and I'd like to thank our team of authors who were willing to kind of participate in this journal club meeting. And I thank you for inviting us.